Hey everybody, in this video I'm going to talk about how we can use principal component analysis of satellite images as an aid to image classification. And we're going to take this as a very high level. This is very introductory, meant for people who don't want to deal with the math but maybe still want to be able to use principal component analysis as part of a project. Much of what I've taken here is from two excellent summaries of PCA online. Those are linked here, and I recommend you go read them, and there's many others. So this is something you can really teach yourself about pretty easily. So just to set the stage, what are we trying to do in general? Our goal is to classify a satellite image into classes using spectral information. So this is a Landsat image. It's a multi-band raster with a different band collected in each wavelength of light. Our goal is to take this Landsat image, essentially a bunch of different numbers, and actually 5 replicate sets of numbers, and turn it into a classified image in which each surface type is assigned to its own class. So water is a class, burned areas might be a class, and so on. So in order to do this with principal components, the first step is actually to extract the spectral signature from all 5 bands of a multi-band raster. So in this example, maybe this is like a Landsat TM image. That's actually what it is. So let's say it has 5 usable bands, okay? So 1, 2, 3, 4, 5, those are the same image collected 5 times. From each pixel, we can take 5 digital number values, okay? 1 for each band. So each pixel ends up being represented essentially by a data vector, a list of 5 numbers. Okay, we can then, if we do that for every pixel, we can construct a matrix of digital numbers. So the number of rows we'd have 1 row for each pixel, so 1 through n pixels. And then we'd have 5 columns, 1 for each digital number that we extracted. Okay? So here you basically have all your data. It's a massive amount of data because you might have 1 million pixels or something. All your data in this big matrix or this big table, okay? And one way to think about this is that each pixel can now be represented as basically a scatter plot of a value of band 1 versus a value of band 2. Right, so each of these dots is now a pixel, but you may be saying, hey, we have 5 bands, not just 2, and that's correct. So if you could imagine somehow a scatter plot that has 5-dimensional axes, right, that's really what we're going to be thinking about here. And it has n points, right? Each pixel is a point. So that's kind of the starting point for visualizing how we might transform our data with principal component analysis. And the first step in principal component analysis is to essentially make a linear fit to the data such that the line you choose goes directly along the axis of maximum variation. So we're going to consider this in 2 dimensions, but you have to also imagine this line is fitting the data actually in 5 dimensions. But in 2 dimensions, it's very clear, right? The data are spread out on a line, and if we fit a line right here, we can do a pretty good job of predicting, well actually hold on, I'm going to go to the next slide. So if we then rotate that line, right, imagine we rotate that line, it turns out that all we need to do a pretty good job of predicting the value of any of these points is the distance along the line, right? It's not going to be perfect, but you could predict the location of this point simply by knowing that it's this far along the line. So it doesn't capture all the information about this point, but it gets you pretty close, okay? And so that is literally, that linear fit is the first eigenvector. It is a mathematically defined line that captures the most variability, that does the best job predicting each pixel value. If you give it a point along that line, it can give you a pretty good prediction of the value of that pixel, okay? That's the first eigenvector. And of course, we can mathematically rotate it like we just did so that we can basically collapse it to just one dimension, which is just distance along this line. We no longer need, both dimensions, okay? So now, taking the same data set, we could actually mathematically compute another line, which would be perpendicular to the first line. It always has to be perpendicular, and it would capture the next highest amount of variability. Okay, so in our 2D example, that would be this line right here. We already have information along this line. Now if we add in a second piece of information about location along this line, then we can really pretty precisely predict where these data points are. Actually, in this case, we can exactly predict where all these data points are. And the reason is that two eigenvectors, you need the same number of eigenvectors as you have bands to make an exact representation of the data. And one other very important thing that's happened here, because these are orthogonal to each other, they don't contain any of the same information, right? The information about point location along this line is completely independent from information along this line. There's no overlap or redundancy. And that's part of what principal components are. Okay, so if we now know, let's take an example point. We know this point. Well, we know it's, for principal eigenvector 1, it's this far along, and for eigenvector 2, it's this far along. Those are actually called the principal component scores. And we can then plot those principal component scores. So again, we're plotting each pixel and the principal component scores of each pixel. And suddenly this is an incredibly powerful way to distinguish groups. Now, of course, if we're just thinking about a two-component, a two-dimensional data set, well, then it doesn't matter, right? We could have already seen this information in the first plot. But if you have a five-dimensional data set with lots of collinearity and covariance, you may be able to basically visualize differences in that 5D data set using only these two principal components. And that's really what makes it so powerful. In this case, these are properties of irises. So another important aspect of principal components is that, as I explained, the first component always captures the most variability, second component captures the second most, and third, the third most. So what we have here is a plot of basically the percentage of the explained variance, okay? Also known as the eigenvalue for a given component divided by the sum of the eigenvalues. And we see that as you go further out in the principal components, they end up capturing less of the or explaining less of the variance. So suppose you wanted to reconstruct your data set using only 5 components instead of 10. Well, you would certainly pick these first 5 components here, and you might not even need to consider these 10 components. So you've essentially collapsed the dimensionality of your data set from 10 to 5. In our example, maybe we'd collapse it from 5 to 2 because we only started with 5 dimensions. Okay, so in summary, here's some important ideas about principal components. The number of principal components is the same as the dimensionality of the data. So in our example, we started with 5 input bands from the satellite. So we're going to have 5 principal components. And that allows us to fully predict every last data point in the data set if we use all 5 principal components. A principal component score is essentially the distance along that newly rotated axis that we talked about. Eigenvectors, which are the lines that we were fitting, are linearly independent. So they're perpendicular. That's a way to say perpendicular. And thus, each principal component score represents totally unique information, which is absolutely so cool. And that's very different than the bands we started with, right? In satellite imagery, it's almost always the case that a bright pixel is going to be bright in all 3 visible bands, right? And so often you don't need all 3 of those visible bands in a classification scheme because they're basically giving you the same information. So with principal components, we can kind of throw out a bunch of those collinear bands. Principal components have no physical meaning because The scatter plot axes have been rotated, so they have no physical interpretation. And we'll leave it there. Thanks, everybody.